Okay. All right. Hello, everybody. Welcome to the first day one of WaterSoftHack 2026. As we said earlier, mostly in the sessions and yesterday, we are going to focus on cloud computing today, right? This is the start of the technical week. My name is Bijaya Adhikari. I'm going to be, leading the lecture section of the tutorials. And my PhD student, Mihail. Mihail, can you introduce yourself a little bit? He's going to lead the hands-on
Yes.
tutorial.
So I already did yesterday, but if you guys don't remember, I'm Mihail and I'm a PhD student at Iowa. My advisor is Dr. Bijaya Adhikari, and I'm pursuing a PhD in computer science. So I'll be hosting the workshop later.
Okay. All right. So basically, today we'll build some background knowledge of the cloud computing framework, right? So what are the different characteristics of cloud computing, right? Uh, what what is its use case, right? What are the good practices and so on. Here, we do not assume any prior background knowledge in cloud computing, right? But you should think of this as intro to cloud computing, right? So the beginners crash course on cloud computing. And so we'll basically do 2 hours tutorial first, and then we'll do 1 hour hand-on tutorial, right, where you'll follow along what Mihail does on screen. And so that's going to be this afternoon. Hopefully, in the next 3 days, right, we get to get to understand a little bit of cloud A's and cloud A's hybrid computing, and then we also get to get our hands dirty so that you can go ahead and use this on your real research on hydro science projects. So for the hands-on part, right, we'll basically use Jetstream, and we are very thankful to NSF for providing us with the access credits, and using those credits, we have set up Jetstream accounts, and this is what basically enables us to do the hands-on tutorials later. Basically, we kind of want to, help you build a good intuition of what cloud computing is, right? And, have a working mental model, right? And, understanding basically, how the cloud system works so that, it comes naturally to you, right? When there is, any cloud applications on your research. Uh, basically, if this was a real life presentation, I would have asked how many of you have, any, AWS or Google Cloud experience. Maybe you can, uh, raise your hands to show. Okay, we will still see the first slide. Okay, yeah, yeah. So, I'm still on the first slide, Okay, okay. Thanks for pointing it out. I'm basically, giving you the intuition for what to expect. Okay. All right. Let's get started. Okay. What are we going to do in the next 2 hours? Right. We'll walk through the 6 modules. Right. We'll talk about what cloud actually is. Right. So basically, we'll talk about the utility computing. Right. So it's like computing as a service. Right. So you don't it's basically you have a electricity wired to your home, and you pay as you go, right, as based on how much you use. So that's the model. And we'll also talk about 5 ideas that define it. We'll talk about different service models, right? IaaS, this is like infrastructure as a service, right, where the cloud basically provides you with the computing resources, right? It just gives you access to the machine and you set everything up. A platform as a service, right? The cloud infrastructure gives you a machine and also gives you an API. So you can just take your code there and then start building your applications. Or there is also a software as a service paradigm, right? Where everything is set up for you and you just have to take you just have to use things, right? Just you set up your data bucket and start using the software, right? So we'll talk about these things in detail, and we'll talk about who manages what, right? So we'll talk about the building blocks, right? So where do we store, how do we set up the compute, right? How is the storage done? Right? Are there different types of compute? Are there different types of storages, right? How to set up, how does the networking work, right? What is the, okay, why is it going back? Okay, all right. So and how do you, what is elasticity, right? Elasticity in terms of your computational need, right? And how are things how is the cost computed? So and we'll also give you an example, right, for cloud computing for water science applications, right? So we'll also talk about different use cases and water science related challenges like real-time data streamings, right? Open data sets that are out there already, right? And then national how do we do national scale modeling. We'll also briefly talk about our particular platform that's there, right? So we have some credits through NSF access, and we have used those access to set up Jetstream 2, right? So we'll kind of go through how these things work, right? So I think and there is really nice parallel between Jetstream and popular cloud services like AWS and Google Cloud. So if you have some experience here, I think these can easily translate to popular cloud services out there. Finally, we'll do a bit of a hands-on preview, right? So we'll talk a little bit about what to expect and how things are going to go tomorrow, right? So basically, do some preview of edge computing. So meanwhile, if you have any questions, just feel free to type it up on a Q&A, right? So either I will answer it live or Mihail can answer it live or we'll also type your answers as we go. All right. Okay. So the big picture idea of how things are separate. This is a 3-day story, right? It's we have tried to tie things together. So today we'll talk about cloud, right? And we'll basically in the afternoon session we'll pull live river data, right, and try to run a forecast on a rendered supercomputer on the ground, right? Basically on Jetstream, right? So and you get to see how to do that. On Wednesday we'll talk a little bit about edge, right? And then we'll push the intelligence out to the sensors in the field, right? And then some computation is done there, right? So under some real world constraints. So if you think about edge devices, right, they have limited memory, they have limited processing power, and so on. So you have to be cognizant of those. On Thursday, right? So we'll talk about how do you combine cloud and edge, right? So what is this hybrid framework? And then in the hands-on, we'll try to combine them, right? So and throughout all these three different tutorials and hands-on tutorial, right? So in all of them, we are trying to basically build a real-time flood early warning system, right, from a network of USGS stream gauzes, right? So hopefully this as you are very very familiar with the application, hopefully this helps you build intuition when it comes to cloud and edge computing. Okay, all right. So right, so okay, why is cloud important, right? So this is something that we talked about yesterday also a little bit, right? When we tried to set up use cases of cloud for hydro science. So as we said yesterday, water emergencies are real-time computing problem, right? So there is when the river is rising, right? So the you kind of want to make predictions before the event happens, right? As the river rises, the value of forecast goes down by a bit, right? So the value of forecast after the fact, that after the event, right, is is very little, right? And how do we make this meaningful forecast in real time, right? And in real time in timely manner, right? Because there are some challenges associated with it. The first is that the data is huge, right? So the data is very very large and it arrives continuously, right? So and it's so yesterday we talked about the four V's, right, in hydro science, right? So as you can imagine, right? The data is large and it it's arriving continuously and it's uneven, right? So the compute there is an uneven need on the uneven demand on the compute resources, right? So the needs spikes exactly when so imagine, right, the rain starts to fall, then all hydro scientists start trying to make forecasts, right? And you get more data because there is more water, so the compute needs spikes exactly when the forecasts are necessary, right? But it's still a very, very important problem because if we take about if you just think of from the monetary perspective, right? So there were about more than 32 billion is the cost of annual US flood damage, right? So it's a very important problem. And also I'm sure the cost on both economy and human lives is significant, right? So this is a significant serious problem and we want to mitigate the risks. Okay. So the old way, right, of solving this problem, right? So how do we so this is a water emergencies are real-time computing problem, right? So how do we solve the problem? So the old way was you basically go ahead, buy a server, right? Big build a very, very big server, right? And watch it stay idle for the 90% of the time and start when the storm season comes, then use it, right? But as you can imagine, that's not a very good model because one, the large servers are very, very expensive, especially now because the RAM prices are right, the chip prices are off the roof, right? So it's very expensive, right? And also where this model wastes a lot of compute power, right? Your machine is staying idle for 90% of the time. So, it's not you have spent a lot of money, right, on the server and it does nothing and it just sits there for a long chunk of time, right? So this is not great. So, okay, how do we overcome it, right? So, cloud computing, right? And it's elasticity is an answer to this. Okay. Now you may say, okay, let me not buy a big server, right? Why can't I just do it in my laptop? Right? But as we talked yesterday, the data is too big, right? There's no hope on being able to do these computations on a small machine, right? So the national data sets are terabytes, at the scale of terabytes. They do not fit on a laptop, no way, right? They also do not fit on a small scale single machine servers, right? As we discussed yesterday, right? So and there is a real time pressure, right? So there is a new readings every 15 minutes forever, right? So batches on the desktops cannot keep up with it. There is a spiky compute need, right? So you need a 64 core for one afternoon during a storm and none the next week, right? But your machine which typically handles normal things might only have 8 cores or 16 cores, right? So when the demand on the compute increases, your local machine may not be able to handle it, right? And we also want to make sure reproducible, right? So we want to make sure the code adheres to a standard, right? And it can run on any given machine. Okay, so what are the concrete outcomes, right? So explain what cloud computing is today, right? Tell IaaS, PaaS, SaaS apart. Choose the right compute and storage for a water workflow application. Log into a real research cloud, right? And then run a live data notebook. This is this afternoon. And then reason about costs, right? And understand the costing model so that you don't rent a very, very big machine and let it run for a whole afternoon and then spend thousands of dollars doing that, right? So we want you to be able to understand these things in detail. Okay. All right. So now, let's talk about what cloud computing actually is, right? So the central idea behind cloud computing is computing as a utility, right? So for example, right, in our home, right, so we need electricity to run all of our appliances, but we do not own a power plant, right? We plug in, right? Our home is connected to a grid system. We plug our appliances in, and there is a meter that kind of measures how much usage was there, right? And we basically use what we need, and we pay for what we used, right? So electricity is a utility, right? And then it became a utility a century ago, and computing, recently, right? Probably a decade ago, did the same thing. right? So the cloud computing is basically on-demand access to someone else's computer, right? So Amazon has AWS, right? Microsoft has Azure, right? So these are like, large systems of computers that reside somewhere else, right? And you're basically like, renting it over the internet. And it's like, so basically, and you pay for it by the minute that you use. And you basically, like give the machine back once you are done, right? So this is like, the utility shift, right? So like, when you own, you buy the hardware, you run it, you maintain it, right? And like, when the machine like, just sits there doing nothing, that cost is on you, right? But when you rent, you request capacity, use it, right? And release it, right? Pay per, like, pay as you go. Okay, so this is the central idea, right, between like, the cloud computing, right? So this is like, computing as a utility, right? So you basically uh, pay for computing, right, as you use it, right? Just like, you do with electricity and like, water, right, and so on, and internet, right? Okay. All right. Okay. So like, does that mean like, any server out there is a cloud computing, right? No, like, we as a like, I guess community, right, have decided like, certain characteristics make it cloud, right? The first one is, right, it has to be on-demand self-service, right? The user has to be able to get resources by themselves, right? In minutes, right? No, like, once like, some formal paperwork is done, right? You have to set account, you have to set credit card and so on. After that it's done, it has to be on demand, right? It has to be accessible very, very easily, right? So like, no bureaucracy involved. So there has to be broad network access, right? You should be, right, the user, right, like, your client, right, and then the client's user base, right, should be able to reach these services anywhere, right? It cannot be that, like your like, cloud computing resources are accessible from Iowa and not from South Carolina, for example, right? So that doesn't work. Resource pooling, right? So many users, so there is a one huge pool of resource, right? And like, the users like, get to share that resources, right? Basically, depending on the client's needs, right? And the provider has to slice it up, right? So basically, this is done through creating different virtual machines and so on. Rapid elasticity, right? So the users, right, or the cloud services clients should be able to scale up the computing, right, and like, scale it down automatically, right? If there is a higher demand on the like, on the client's application, client should be able to easily scale it up, right? So like, and then if like, your client doesn't have like, very high demand, right, they should be able to scale it down. So imagine like, you are running a e-commerce software, right? So when you rent a cloud services, you can imagine, right? During Christmas, everybody is trying to buy like, a lot of products, right? And the like, so a lot of people visit their website, so the demand goes up, right? And then the cloud service should be able to handle that automatically, right? And then after a while, right, our holidays are over, all the shopping is done, nobody is running like, going to the like, February is like, dead month for e-commerce, right? So like, everybody scales like, people do not go to the like e-commerce websites, right? Hence the like, the demand on the e-commerce website goes down, right? So the web service should be able to handle it by scaling down the resources, right? And everything like, has to be measured, right? So everything like, the usage is metered and the client pays, right, for based on the usage, right? So these five things, right, make a computing system a cloud, right? Cloud computing. So this is like, basically, so these definitions, right, these characteristics of cloud come from NIST. This is the US standard body. If a service of has all five, it's a cloud, right? If it is missing self-service or elasticity, then it's just somebody else's server, right? Then it's not really really cloud, right? I mean, so like, these character once all these characteristics are met, right? So this is like, what we define as a cloud computing system. Okay. So like, let's like, do like, let's do an example, right? So like, to build intuition for cloud computing again, right? So like, let's imagine, right? So you are thinking about like, whether you should like, you have to drive every day to your work, right? And then you are basically thinking about should you buy a car or call a cab, right? And you are trying to like, basically, build the like, the pros and cons list in a sense, right? So you have to think about upfront cost, right? So the big, like, if you buy it, right? So there is a, like a big capital purchase, right? But if you rent it, there is nothing else in the beginning, right? There's no upfront cost. So this is like, owning it is like buying a big machine, right? And then like, calling a cab is like, doing things on cloud. Time to start, right? So if you have to buy a car, right, you have to go to the dealer, right? You have to think about go to the bank, right? Get a loan or like, have the payments ready. So it may take some time, right? But if you just have to call a cab, right, it takes minutes, few minutes, right? So it's the same, right? So if you have to buy a big server, right, there's a wait list. You have to like, get all the parts in. You have to like, set the servers up. You have to connect it to like, you have to make sure that, your connections are on, your internet is on, right? You have to then like, install whatever is needed, the right OS, right? The right APIs and so on. But, for cloud, you can just like, set things up in minutes. So the idle west, right? So the cost of like, resources sitting idle is on you if you own it, right? So for example, your car, like, let's say, you have a like, 2 months vacation and you don't like, or like, and you go somewhere else, but and your car is just parked at your home, right? So the car is a resource, right? Where you have spent some money, but it's just sitting there idly, right? So that cost is on you, right? I mean, the car just sitting there, like, there is some depreciation, right? It loses value, right? So that cost is on you wherever, but like, basically, on the cloud, right? Or like when you call a cab, you play only when you need it, right? So the idle time is not on you, right? It's on like, whoever is like, whoever owns the machine or the car. So scaling up, right? Let's say like, for your like, you're like, like, in this example of car versus calling a ride, you're some like extended families visit, right? And you have a 5 car sedan and now it doesn't fit, right? You have to buy another car, right? So, so like, that's like, so it's like, scaling up is hard, challenge, more challenging, right? The same thing in like, when you own a machine, right? You have to buy more hardware, right? You have to like, so there is like, it's almost like a, like, redoing the upfront cost again, right? So maybe slightly cheaper, but, almost like that. But, like, like, it's a lot easier to like, scale up, right? So instead of Uber, you'll call Uber X, right? Or instead of Lyft, you'll call Lyft XL, right? So that's it, right? So you like, when you rent it, it's a lot easier to scale up. Maintenance, if it's your car, it's your problem. If it's your computer, that's also your problem, right? But when it's like, the cab, it's the like, the provider's problem, right? Whoever owns the taxi has to fix it, right? It's not your problem if the car breaks down. The exact same thing, right? If the underlying infrastructure fails in cloud, that's not your problem, right? You don't, I mean, like, it could be your problem in a sense that, your application breaks down, right? But, it's provider's responsibility to maintain it, right? And like, provide alternatives. So, but, like, why do we still buy cars then, right? And why do people buy cars? Well, like, when there is a steady, predictable, like, need, right? Then it's better to own because it's typically like if you own things, it's like, for a predictable, steady demand, it's a lot significantly cheaper than renting, right? So if you own a car for your like, daily commute, right? It's cheaper than, like, getting taxi wherever you go, right? Because, you know how much you travel and so on. But for like, bursty, exploratory and collaborative things, right? Like, but renting is better, right? So for example, if you go on a vacation somewhere and in that city, right, that, the demand, your demand for like, transportation in that city is burst in a sense, right? So like, you only like, have demand when you are there, right? So it's better to like, rent things. Okay. All right. So, like, so now there's like, something of a loop going on here, right? In 1960s, right, there were these big mainframe computers, right? There was a one giant shared computers and users basically rented time on it, right? They would physically go to the lab, right? And, they would get time in the machine, they would do some compute and then like, leave the room. Then, in the 1980s, it was the era of personal computer, right? Everybody had their own personal boxes, right? In 2000s, right, we started getting back to the data centers, and then the public cloud started in 2006, right? And today, most e-commerce applications, right, big scale, web services, they're cloud first, right? A lot of these things reside in the cloud and are uh, like you know uh, cloud first. I thought there was a question. Okay, so Mihail, you are answering the questions.
Yes, I'll be
Okay,
typing.
okay, all right, thank you. Yep, sounds good. Okay. So, right. So, who runs the cloud? Who owns the cloud? Depends on which cloud you are talking about, right? So, on the commercial side, I think we you guys might be familiar with these things, right? AWS is one of the biggest cloud providers. There's also Microsoft Azure. There's also Google Cloud Platform, right? And here we pay with a credit card at scales, and then these are huge, very powerful, right? But they are also expensive, right? So uh, um, the costs can rack up very very quickly. Here, right? So for our training program, we have we're basically using the National Allocation Program through NSF Access, right? NSF is the National Science Foundation, and so through that credit, we are going to use the system called Jetstream 2. It's a research cloud system based in Indiana, right? And they have systems like Anvil, Expanse, Breeze, Delta, so on and on, right? So here, we basically, so NSF has given us some budget, right? And then we in forms of credits, and we can export our credit to Jetstream 2, and then we pay with this, right? So so academic, so this system that we're going to use is built for science, right? And for academics, right? So it's free to to some extent to funded researchers. Okay. There was a hands up, I think. Is there a question? Can the uh am I still sharing my screen? No? Okay, I think I okay. All right. Okay. So there was a hands up from a participant. If there is a question, please just, type in the Q&A. I don't know how to how to enable your uh enable you to ask questions. Okay. All right. Okay. So all right. So what is cloud, right? In a sense, right? So uh, let me so the the cloud computing, we just basically say it's connected through the internet, right? That's what it means, right? I mean, there's the computing service does not really really live in the cloud, right? It's a very real building. It's a warehouse basically full of computers, right? Tens of thousands of them, and with industrial power, right? And it has this all these characteristics that we talked about earlier, right? It has industrial level power, cooling, network, right? And that someone else manages and someone else runs, right? And make sure the electricity is connected to, make sure the cooling systems working and so on. It's a real physical object, right? It's just connected to us through internet, right? So in a typical data center, large scale data center, there are more than 100 plus servers, right? Which are physical machines, 100K plus, right? And it's it's staffed always 24/7, cooled, monitored, right? And there are multiple backup powers and network paths and so on, right? So this is a real system, right? So when we say your notebook runs in the cloud in Indiana this afternoon, this is a literal building in Indiana, right? Like the University of Indiana, I think. Oh no, sorry, IU, Indiana University, right? And it's full of racks, right? There is somebody actually has built all of these things, right? And somebody is actively managing it, right? So the provider, right, the Jetstream 2 providers, they will absorb all the hard, boring, expensive parts, right? So power redundancy, cooling, physical security, right? Everything that has to done, right? So because they are they have spend so much upfront cost, and they rent it out to many academic programs like us, right? Hence this amortized cost, right? Well, this basically expensive thing exists and everybody uses it, right? This is what makes it cheaper, right, than renting for most of us. Okay, all right. Okay. So now, how does, how do we, slice one sorry, resource into multiple resource, right? So this is called virtualization. Basically, one machine can be, simulated to become many, right? You have a multiple simulated machines in single machine. It's called, virtualization, right? So imagine this, this blue box is a one physical server, right? We have the first virtual machine inside it, right? It has its own operating system, own applications, and own resource definitions, right? Similarly, there's another virtual machine 2, virtual machine 3, virtual machine 4, right? VM1 can be rented by somebody, VM2 can be rented by somebody else, VM3, and so on, right? So the VMs are actually software, right? So it's a virtual operating system, right? So it's basically it's a virtual machine in a sense, like there is a machine, right? And you simulate another machine inside it, right? And then you install whatever is needed. So the each virtual machine, so this is um, if you have some computing background, I think you kind of understand it. But all you have to know is that each virtual machine behaves like its own own computer, its own operating system, right? And it's not it's not allowed to access the other virtual machines, right, running on the same system. So it's for us, the users, it looks like a standalone machine, right? So why does it matter? The the provider will fill the idle capacity, right? And it will basically rent out to multiple different people, and we get exactly what we need, right? Depending on our need, right? Let's say there's a very big physical server and we don't need everything, right? So all the compute power that it provides, right? We just need a small chunk, right? So we'll just rent a small VM. Okay. So just I want to so in this afternoon, right? So we'll basically see you can pick a size of a computing, right? And I'll also do some example, right? And this is how we are able to pick the size resolution would make it okay, the cloud has multiple different computers with a lot of different options, right? But usually it's done through virtual machine, right? So this is what allows us to pick the size, right? As you'll see this afternoon, right? And what we need to understand is we're basically asking for a small slice, right, of a big machine. Okay, so what are the different service models, right? So let's say we rent VM1, right? So this particular machine. So now basically the question is do we want to do everything from scratch, right? Do we want to have access to API through the provider? Do we want their software that the provider has built? Right, so these things basically determine the service model. Okay, so at this point, any questions? Q&A. Okay. Uh,
So they asked the previous question on how to work with sensitive data, and I told them they should either process it locally or if it's too big, encode it first. So now they were asking if you know any kind of encoding that's used.
okay, yeah, I think you have to be very, very careful with sensitive data, right? So basically, you are renting somebody else's computer, right? So if it's a sensitive data and there are restrictions associated with the data, I think unless the the service provider meets those criteria, you cannot transfer it to them, right? So one example is let's say I run a hospital, right? Or we run a university, we are in a university, right? So the students' grades and students' data is protected, right? And so you cannot take that data and move it to AWS, right? So you'll you'll be violating federal uh, uh, policy there, right? So you have to be very careful, right, with the sensitive data. right? So basically, it's like taking your birth certificate and leaving it in Airbnb, right? So that's not uh, uh, a very smart. Okay. All right. So let's move on. Okay. So so basically these three service models are trying to tell you how much management you want to do basically. So in the infrastructure as a model, right, we get the raw machines, right? We get the not real machines, right? Again, a virtual machine, right? And then so basically, you we get the raw machines and you kind of install and manage everything, right? So you get the virtual machine, a slice. It looks like any standard a Linux machine, right? Once you SSH into it, and then you install everything. You install your Python environment, right? You install you install the packages, right? You build your APIs, and then you build application, right? Maybe you build a web application, and then your users can access it from there. Or platform as a service, right? So you basically get a managed place to run a code or a database, right? You just have to build your app on top of it, right? So the the database systems are there, the APIs are there, right? So everything is already there, right? So it's like a Google Colab, for example, right? You just have to build your app, right? Or you build it locally and you take your app to the cloud and then run it there. On the other hand, software as a service is you get the finished app, right? And you manage nothing, right? So for example, these are your uh, um, uh, example is an email, right? Gmail, right? So it's still the system lives in the cloud, right? But we don't code, we don't do anything, right? The application is already there and we just use it, right? So for example, so if I think Shopify, right? So you are still trying to be sell something, right? You are trying to build a business over cloud, but everything is set up there, right? So there is a back end for merchants. You list, make your items, right? You mix list your items that you're trying to sell, right? And it's displayed to your users, right? So but no coding involved, right? The software development is already done by the providers. Okay, why does it keep moving? Yeah. Right. So today, I think we'll mostly do IaaS, right, on Jetstream 2, right? So, but the Jupyter Hub that we're going to use is closer to platform as a service, so, from your viewpoint, right? So so Mihail has done the hub, he has he started with IaaS and he has set up few things up, right? So that you can do coding on Jupyter Hub, right? So from your viewpoint, right, the the fellows and trainees viewpoint, it's closer to platform as a service, right? But if you have to do what Mihail did last week, it's closer to platform as a service, right? So today you just you'll get a notebook, right? And then but you do not need to manage the machine, right? And you'll basically start coding, right? You'll load real-time data from Hydro Science application, right? And you'll do the river uh, flow forecasting. Okay. So in the infrastructure as a service, right? So basically it hands us the raw ingredients, right? And then it basically gets out of our way, right? So there is nothing else there. So you get a machine, right? You pick a number of cores, number of RAMs, GPUs that you need, and so on, right? The operating system boots, and then the entire thing is ours, right? So it provides us with disks, right? Either attached disks or access to some storage buckets. The the networking is also provided, right? We have a public address, we have a firewalls, we have secure login. Everything is provided by the cloud, right? And then it's full control, right? We have to install any services, any software that's needed, any library that's needed, right? Any version of the packages that's needed, we have to basically do it on our own, right? So in a sense, everything that we do in this afternoon lives here, right? So we'll launch a virtual machine, right? We'll attach a storage and open a port for the notebook server, right? And then after that, the students can then make some development there, right? So in a sense, this is why is it useful? It's the control is it's basically like having your own machine, right? So where you are the administrator, right? And you can do there's no restrictions here, right? So you don't have to call somebody to ask them to fix their APIs, right? To adjust for your application, right? So you can basically do whatever you want here. But sometimes you may not want to do that, right? You may not have the Linux expertise, or you just don't want to like you know spend your afternoon installing packages, right? So you might be like, okay, you know what? I don't want to set up. I just want to code, right? I'll bring my code. You the provider do everything for me, right? You set up the machine, right? After that, you set up the APIs, install Python packages, right? Everything, right? I just give me the APIs, and based on your APIs, I'll make my application, right? So the platform as a service, in a sense, like it manages the machine, it manages the operating system and the runtime for us, right? And we just hand our code or queries, right? And it does everything else. So what's the trade-off, right? So here we have less to manage, right? So like a smaller company can do it, for example, right? A small hydro science team can do it, but we have less control, right? If the platform does not support a library or version control, right, you can be stuck, right? Or you have to there's rounds of email exchanges and so on, right? So the convenience, kind of it's convenient in a sense that you don't a lot of work is handled, but it comes at a cost of flexibility, right? So it's great when you want to uh, get for first for getting started, right? Or nowadays for ML training services, right? That's pretty standard. You have your data, right? And you kind of know how the framework is going to look like. So then it's also pretty good. So if your application falls on on the norm of more of the standard application, then I think there are very good platforms as a service out there, right? Whereas you're trying to do something something new, right? Where existing packages do not work very well, right? Or they need significant extensions, right? You might be better using as going with the previous framework. Okay, so software as a service is basically is how our world is running nowadays. So sorry. Let me. All right. Okay. Yep. So all of our popular applications, right? Gmail, Google Docs, right? Outlook, right? And even I think Facebook, right? So social medias and so on. And these are all applications that live in the cloud, right? So the apps are finished, right? They are designed with the specific users in mind, right? And the users just use them, right? No coding involved, right? So, a lot of water science tools that are already out there, they are also software as a service in a sense, right? So, HydroShare for sharing data and models, Quasi, right? So, where Tony, who's in the meeting, is from, right? So, they're a client for pulling observations, right? Google Earth Engine for planetary scale remote sensing, right? So these are all services that already live on cloud, right? So these are all software as a service in a sense. So it's fantastic when finished tool, right? So that already lives in the cloud does exactly what we need, right? So we don't need to build anything, right? I just need a way to send messages to Mihail from time to time. I just use Outlook, right? I'm not going to start with a black box machine, right? I'm not going to install everything, build my email server, email clients, and then send message to him, right? So that's too tedious. I'm just gonna use existing machine or existing service, right? But if these things are not out there yet, then we might want to build our own things, right? So we'll revert the river we'll revert back to either uh, uh, platform as a service or infrastructure as a service. Okay, so what are the difference between virtual machines and a container? Virtual machines, it carries a full operating system, right? It's slightly heavier, right? Gigabytes in memory, right? And it boots in minutes, right? Because it's it acts like a real machine, right? There's a strong isolation, right? So it's like it's almost like an independent machine, right? So it's like a best if we want a durable machine, where we have like ultimate control. What's a container? Right? A container is like basically it's a system that lives within a host operating system, right? It's light and it packs like the softwares that we need, and like the it also provides version control, right? So this is for like reproducible portable workflows. So the a famous example of a container is a Docker, right? So which is basically like a container that like bundles the code and exact libraries and versions as we need it, right? So this is also like I mean some providers like will provide containers, right? And instead of a virtual machine, so you just need to like know the difference, right? So virtual machine, basically you are getting a small slice of machine that acts as an independent machine, right? Whereas like if you rent a Docker, sorry, a container, then you are basically like buying a system that lives in a host operating system, right? A small scale system that's like not an independent machine, right? But like is a system that kind of lives within a machine. Okay. So, what's Kubernetes, right? So, like basically, again, I think like we hear it a lot, right? So you probably have heard it, right? And so we kind of want to like make sure that you understand what it is, and like so like when you have a lot of containers, right? There has to be something that holds them together, right? And then like and then that has to manage the entire framework, right? So some containers are not needed, right? Some containers are like dead, right? So you have to like do the management of these containers, right? You need to recycle them, right? Like you need to like basically like once usage is ended, right, you have to like reboot them, right, restart them, and then like basically manage the entire thing. This whole like the thing that orchestrates this whole entire thing is Kubernetes, right? So it's very powerful, right? And like is quite useful, right, for like and basically allows us to like manage resources more efficiently, but it's not needed, right? So if a CS leaning fellow wants to go deeper, right? You can go to like the NRP's National Research Platforms. Like they have a tutorial there, right? So once you finish this hack, like WaterSoft hacked workshop, you can go there and learn more about this. Okay, so let's talk about the building blocks for a bit, right? So like basically like uh, like what kind of things. So now we understand what a cloud is, right? What kind of computing system is called cloud, right? And what kind of different like varieties of clouds are out there, right? So now let's try to dig deeper into like what exactly like makes like what exactly makes up the cloud, right? Okay, at this point maybe like I want to like check if there are any questions. If there are any questions, please feel free to type them, right? Or raise your hand. Okay. All right. If not, so again, right? So let me recap what we have done so far. We defined what is cloud computing, right? What are the characteristics of cloud computing, right? What's the difference between a server that's out there, right, and the actual cloud system, right? And we talked about like how like what are the different frameworks that fall under cloud system, right? So depending on like how much work you the like user has to do, right? Now we're going to talk about like what are the things that make up the cloud, right? So we'll talk about compute, we'll talk about storage, we'll talk about network, we'll talk about elasticity and cost. Okay, so basically, right, so the flavors or instances are basically like just like are like basically the define the size of the compute that you need, right? Think of them as a like a t-shirt sizes, right? Do you want a small, medium, extra large, extra small, and so on, right? So we kind of want to like build a like once you like get started, right, and then like you start using clouds heavily, you kind of want to like build a habit of picking the smallest instance that kind of does the job, right? Because if you pick the larger instances, they're going to be more expensive, right? But if you pick a very, very small instance, they may not do the job, right? So you kind of want to pick the right instance in a sense that you want to pick the smallest instance that can do the things for you, right? So an example, so these are from uh, I think these are the instances from Jetstream, right, Mihail? Yep.
Yes.
So m3.xl here, right? So if you pick this instance, right, there is like a 32 cores there. The memory is like 125 GB. Does it have GPU? No, no GPU. I think they
No.
have like GPU instances are probably separate,
Yes.
right? And this is where our shared Jupyter hub that we're going to use this afternoon lives, right? So if you so let's say the number of fellows are too small, right? It was just me, Mihail, and three other people would have probably picked M3 quad, right? Where four cores, 15 gigs, right? That's one single user notebook and would take tons, right? Just doing the examples, right? So basically each cloud provider will have the list of instances that kind of define how many compute resources it provides, right? So the things that you should check for is the number of cores, right? And then the cores also have their basically how much powerful core is also part of the description, right? How much memory does the system have, right? And what kind of memory it has is also defined. Does it have any GPUs, right? If you want to do more powerful machine learning on the cloud, then you want GPUs as well, right? So you have to check for all of these things and then pick the right one. Okay. And the next thing to remember is the machine that you pick, right? The more larger machine, like more powerful machine you pick, right? Higher the rent is, right? Higher the cost is. Okay. So you kind of need to also understand when you need the GPU machines, right? The CPUs are very they basically provide a few fast, flexible cores, right? So it's good for most kind of data, right? And branch computing. It runs almost anything, right? All the computing that can be done in GPU can also be done in CPU, but GPU is faster for certain computation, right? So ML like computation in a sense, right? So our nowcast trends fine on CPU, right? So the example that we're going to do today, right? So this is just going to be on CPU. So GPU has thousands of small parallel cores, right? So it's great for single instruction multi-data kind of computing, right? So where there is a one instruction that has to be repeated a lot of number of times for multiple different data, right? So it's good for multiplying matrices, right? Multiplying vectors and so on. So it's amazing for deep learning algorithms, which are basically sequence of matrix multiply and tensor multiplications in a sense, right? But GPUs are also more expensive. They cost more, right? And so you only want to rent GPU machines when you know for sure that you are going to use GPU, right? So all GPU machines will also have CPUs, right? So if you don't need GPU, just rent a machine that only has CPU, right? And don't rent a GPU machine. Okay, so there are there are three kinds of jobs in a sense, right? So a block is it's like a so for a storage, right? So where do you store the data, right? So the cloud, uh, essentially, if you think about it, you're just renting compute instances, right, to process your data. But where does your data live, right? So the data needs a permanent place to sit, right? So there are basically three kinds of things, right? So one is a block, right? So it's like a normal disk attached to your virtual machine, right? And it's fast and personal. It's but you need to have maintain a VM that's connected to it, right? In a sense, it's kind of like your home folder or database, right? And so on. And there's this objects, right? Or for AWS, people call it buckets, right? The same concept. So it's basically a giant web accessible bucket of files, right? So these are usually very big and shareable, right? And so a lot of public data sets and backups reside on objects. But these can also be they can also be private, right? So like, there is a control that like, kind of like, every web provider, will let you define the object or like buckets to be private or public, depending on like, the access level you provide, you define. Right. The other like kind of storage is file. It's a like basically a shared folder that many machines mount at once. Right. So like we have a small system in our group at Iowa, right? That Mihail and I and other folks like from our group use, and we have a like few machines, right? 3 or 4 machines, and there we have a shared memory folder for our home disk, right? So it's like it's mounted once, but we access it from multiple different machines so that the home directory looks exactly the same no matter which machine you log into, right? So this is what the file is. Okay. All right. Right. So one thing to note is that the biggest water science data sets, they already live in the cloud, right? So we don't download this into cloud, right? So we basically like, do the analysis on the cloud. In a sense, we bring the code to the data, right? And then like, read only the slice that we need, right? So the National Water Model, the full forecast archive is on AWS, right? It's on S3 bucket probably, right? USGS and NWIS provides real-time gauge readings over an web-based API, right? So this is already on the cloud. NOAA and satellite data, like for example, like, radar data, HRR, weather, and imagery, right? They are also like hosted as a open source cloud data. HydroShare, this is also a community data sets and models, right? This is also shareable by link, hosted in probably one of the so okay, this is I'm not exactly sure where it's hosted, but it's accessible right through cloud. Okay, all right. So we are hitting the 1 hour mark. Any questions so far? Okay, if not, let's take like a 5 minute bio break, right? And we'll resume.
There is a
Uh,
question,
there is a question. Okay.
Bijaya, in Q&A.
I don't see any question that's not answered. Do you see any? Uh,
Yeah. Is it a good idea to store a file inside a virtual machine in case it's shared or a virtual machine not shareable at all? That's the question.
where is it? I don't see it.
In Q&A open?
Oh, open. Okay, okay. Okay. Is it a good idea to store a file inside a virtual machine in case it is shared or a virtual machine's not shareable at all? So, like, okay, so the virtual machines, in a sense that, if your team rents it, right, then, like, multiple people can access it, right? So that's like, feasible. So usually, when we think of a file that lives in a cloud, right, the data that lives in a cloud, it needs its permanent location in a sense, right? So like the storage and compute are two different things, right? The compute kind of provides you like access to CPUs and GPUs and like local memory, right? The RAMs, right? That you need to do something. Storage is like places give like the kind of things that we talked about, file and like buckets and so on. They provide a home for the data, right? And the different types of so like if you need a place to like permanently store your data on the cloud, right, you have to pick one of these three different kinds of like data storage, right? Now this is independent of which instances you rent to process them. So if it's a one-time thing, right? If it's a one-time thing where you rent a virtual machine, load your data to the virtual machine, do some compute, right? And you don't need to host the data permanently. You can just move the data to the virtual machine, right? Using SCP, blah, 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 right? And then do some processing there. And then you get out of the machine, return the machine, data is lost, right? Data is done. You don't need it, right? Anymore. But if you want the data to be like, permanently accessible, right? Like, the NWS forecasts, right? Which already has to be, which always has to be accessible, right? To many different people, then you have to use one of these three frameworks, right? So these things are probably like, stored as an object, right? So the hydroscience example that I gave. Does that answer your question? Henok, thanks for the great question. Okay. All right. So let's take a bio break for a while, right? And then it is 11:01. Like, let's resume at 11:10. Okay. All right.
It's 12 in Eastern
Okay.
Time, Bijaya.
Okay. So like 12:10 Eastern time. Okay. We'll resume, basically we'll resume in 9 minutes.
Yes, thank you.
All right. Thanks. Okay. All right. So it looks like there is a question in Q&A. The question is, any idea about affordable cloud storage for big data? Already tried Google Cloud, but came out very expensive. Yeah, okay, that's a great question. I'm not, so I think probably Azure and Google and AWS have very similar pricing, right?
Also, it depends what you use it for, how big is the actual data,
Mhm.
and for how long you need to store it. If I remember correctly, Google Cloud, because we're affiliated with universities, they give us like a year for free, and you have terabytes of storage. So you may want to look into that.
Yeah, so the AWS also has some academic credits. Not probably Microsoft has, but I've like never used it. So if it's for like your research, right? So then there are I think manageable pathways, right? And I think there are some you can submit them there are research proposals also, right? That these companies holds and they give you access to the cloud computing, right? So maybe that's an alternative. But as you said, right? This is if it's for the cost is it's there was time when it was cheap, right? When the the companies and the investors were
If
taking
it's also like if they just want to process it on the cloud, you can just get something like this, like a small SSD if it's under a terabyte, and
Mhm.
then interface it with the cloud.
Okay, really? So who handles the network? You send it through your machine.
Yeah, yeah, it goes through your machine, yeah.
Okay, all right. So let's continue, right? So as we said earlier, the biggest water data sets already live in the cloud, right? So that's where we're going to take our computing to. Okay. All right. So, how do we reach our machine, right? And how do we secure our machine? So so there are public IP addresses, right? So this is basically the address of our virtual machine, the machine that we have rented in an internet. It's like a phone number for computers in a sense, right? The connected to an internet. So there are so we'll use to log in securely, we'll use SSH encryption, right? We'll use SSH key and not regular passwords. So we'll have to set up a security groups, right? So a firewall, open only the ports that we need, right? Close the rest. So the the ports basically tell you you when you build a system, you kind of know, right? So which protocols you have to use, that kind of informs you which ports you need to open and which ports you need to close. So only don't keep everything open, right? So for example, if right, you are going to host a web service, right? Then you might want to open port 80 or 443, right? If you're going to SSH into the machine, right? You might want to keep port 22 open, right? So you want to take these steps to mitigate the risks. But this is only if you do infrastructure as a service in a sense, right? If you do platform as a service or software as a service, then you don't have to worry about these things, and the provider will uh, take care of these things, right? But we should always be concerned about the security, right? So it's kind of we rent an Airbnb, right? We want to make sure the locks, right? The doors has locks, right? It locks from inside and so on and on, right? And we want to close all the windows and so on, right? So an exposed machine is always a target, right? So we just want to lock everything down and just keep the right door open, right? To make everything is safe, right? So that's the biggest takeaway. It's not a security course or anything, and we won't talk deeply about how to do these things, but this is something we should always have in mind when we work with cloud. Okay, so the superpower of cloud computing is elasticity, right? So basically, is it is the main reason why cloud beats owning a single box, right? Single machine. So basically there are two flavors, right? So we can scale up to swap a bigger machine, right? When the needs grow, and we can scale out, right? And meaning we can run multiple machines in parallel, right? So this chart is a real result from the workshop notebook. So that we're going to run in a bit. So if there is a one core machine, right, and if we just use one core, one of the only one computing core, right? So to train now custom model on 60 gauzes will take 180 seconds approximately, right? If we do it on 8 cores, it takes 32, right? And then it takes only 23 seconds if we use 32 cores, right? So basically, it's the same code on the same machine, right? Using all cores instead of one, right? So cut the job from 3 minutes to 23 seconds, right? But if the latency of 30 seconds, around 30 seconds is enough for you, you might just want to use 8 cores instead of 32 cores, right? So you see, right? So depending on how much resources you use, your compute times can go up and down, right? And as a system engineer who is building these applications, we kind of need to be uh, cognizant of this, right? And take advantage of this elasticity, right? And the power that cloud computing gives up, right? So we can either scale up, right, or scale out, right, and then release it, right, once the demand is down, right? So the rent capacity for the peak hour, right, and increase the capacity for the peak hour, right, and then scale it down, right, so that you don't pay the heavy price for uh, uh, the whole year, right? So are we going to do this, Mihail? Are we going to run in the same code on one core, 8 cores, and 32 cores this afternoon?
Yes. We're
Okay.
gonna see we're gonna see like elasticity in real time.
Okay, so that's going to be amazing. All right. Okay, so reliability, right? So that's something that cloud has to make sure, right? So we can for an operational flood warning system, right? So this is a requirement, right? The system has to be up, right? Precisely during the disaster, right? When things are when network structures are falling down, right? When the flood is sweeping things, that's when you need it up, right? That's when it's most important. So reliability is one of the key characteristics in hydroscience, right? So this is something that we care about. So the cloud, in a sense, gives us resilience, right? That we cannot give it by ourselves, right? If we because there is redundant machines, right? The machines are these things are spread out in multiple regions and zones, right? So and there is a high uptime, right? So providers usually target a very very high availability, right? 99.9 through basically multiple redundancy, right? And it's also to make sure that it's up, there is managed security, right? So for example, a simple DOS attack, right, or DDoS attack cannot take the entire server down, right? But if it's just my machine, right, I create a simple website and host it on my laptop, right, then I don't have resources to take all the security precautions into account, and Mihail can run a simple DDoS attack to take down my server, right? So there is relative advantage, right, when it comes to reliability when using cloud services. Okay, right. So the now, right, because we are using pay as we go, right? So you have to kind of understand the trap, right? In a sense, right? Everything is metered. Okay, once you use the cloud, everything is metered, right? And there was a great question by one of the participants, right? So if how do we mitigate the cost, right? How do we bring down the cost? So that is something that we have to always think about, right? So nice thing is when things are off, right, it's it's the cost is zero, right? And but on the flip side, right, if you forget to turn it off, right, if the machine is already running, and this is a problem when you're new especially, right, because I mean, you may not take all the steps that's necessary to shut things down. And it has happened to me, right? So when I was a grad student, I took a course on big data, big scale data mining, right? And one of the homeworks that we had was to do things like do some analysis on Amazon Web Services, right? So the course provided some credit, like $50, right? And I had I forgot to turn off the machine, and it ran for 30 30 40 days idle, and I got a bill on my university on my university email, right? And I requested and I didn't have to pay it. But like when you are new, it's it's easy to forget, right? Because you maybe you're not aware, right? And essentially it's easy to make mistakes when you're new to something, right? So a good habit to remember is like you boot the machine, do the work, and then you shelve it, right? You have to also remember the last thing, right? You are so happy, right? So imagine you do the coding, right? On your local machine, it works. Maybe it doesn't work on the cloud. You are frustrated, right? And you make it happen after 3 4 hours of work, and it finally works, and you're so happy, and then you forget to turn it off, right? So it happens. So, but you should always remember to shelve it, right? And we should also make the habit of renting the right size, right? And rent GPU only when needed, right? A costly machine mistake is leaving a 32 core VM running all week by accident, right? And it burns thousands of credits doing nothing, right? So once the machine is rented, right, the provider is giving you the machine. It doesn't care whether the CPUs are actually running or not, right? Once the machine is rented, you are paying, right? So the bill is what you live on, right? And not what you compute, right? So it's basically once you have the machine on your name, you have to pay, right? It doesn't matter whether you are using it or not. Okay, so now let's basically try to talk about what kind of things we can do using cloud computing for water science applications, right? So we'll talk about real-time data, open data sets, national scale modeling, right? And so basically try to build some intuition about the things that we already know. Okay, so any questions so far? Let me check the Q&A section. Okay, I don't see anything there. Uh, okay, so keep the questions coming, right? So there are no bad questions, right? So we're happy to take questions based on your experience, based on your curiosities and so on. Okay, all right, let's go on. So, right, so here so basically, right, so water data, as we talked earlier, arrives continuously from many sources, right, at once, right? And no single machine can ingest, store, or act on the same time, right? So the stream gauzes, right? So there is a reading every 15 minutes, and there is not a single stream gauze, right? A single river system will have I don't know, thousands, right? So there's a lot of data arriving. There is a radar readings and satellite readings, right? Hourly, sorry, continuous, right? I mean, I don't know, every few seconds. There's a weather models, right? You get hourly cycles. There's a field sensors, right, which are also always on, right? So basically, and the value of this data and the forecast that we produce is time sensitive, right? So the forecast is only useful before the flood, right? As we said earlier. So we need these infrastructures to be always on, ingest the stream, and can handle this burst of computing, right? During this uh, during flood events, right? So this is a basically a cloud shaped problem, right? So and tomorrow's age lecture will basically complement this nicely by pointing out that some of these sensors in places with terrible connectivity, right? So some of the stream gauges have a bad connectivity, right? What can we do there? I think I saw okay, there is a question. uh
Oh, I
Oh,
answered.
okay, you answered it. Great. Okay, so let me repeat the question, right? It's safer to switch from 32 core to one core when no processing is run. Is it easy and direct to change? You can, yeah, I think Mihail's answer is right. So you should if you are not running anything, just shelve it, right? You still have your account, right? You can always re-rent a new machine, right? I mean, your everything is there, right? When you need it, you can just rent it,
So also like some cloud providers like Jetstream are very nice. Like I didn't shelve it for some time and it didn't take any credits for it. So some cloud providers actually only take like waste credits on you only if you use the compute. But do not trust AWS and the big ones. They will make you pay.
I mean,
So
it's like a good idea to always not occupy resources that you don't need, right?
yeah.
So even if they don't charge you, they be if there is somebody else who needs it more, it's better for them to be to have the resources available to them in a sense. Okay, all right. Okay, so the open water data that we can pull up today, right? So these are basically the data set that we said earlier, that we said already lives on the cloud, right? And so once we share the slides, I think this is a good slide for you to keep for your references for your projects, right, that you want to do later. Right, so basically we do not need to generate data, right, to start water science research in the cloud, right? So these enormous high quality heterogeneous, right, high resolution public data sets are just one API call away, right? So these are obvious starting points for your for the fellows at least for their capstone project, right? And this afternoon we'll use the USGS data, right? We'll try to pull a live stream flow data, right, from today, right, Mihail? We'll
Yeah.
pull today's data from
Yeah.
USGS, right, and then try to do some flow prediction, right? And that hopefully is a good example for you to get started with. And the other thing is all of these data sets are free, right? And they have a lot of publications accompanying them and citable and so on. Okay, so uh, what is big, right? So petabytes of data every hour, as we said earlier, right? And a lot of data points, right? So 2.7 million river reaches forecasts, for example. Okay, so what kind of project are we going to do from in the afternoon, right? So we'll basically try to build a flood early warning system, as a nowcasting approach, right? So we'll first ingest the data, we'll set up the cloud, right? Where in Jetstream, right? We'll create an instance, right? We have a Jupyter notebook hub, right? And then we'll write a Python code to ingest the data, right? So we'll pull live data from the NWIS, right? And then we'll load it in our cloud machine. Then we'll run a nowcasting model, right? We'll basically develop it right together, right, step by step, and then we'll implement it and then we'll run it. So and this model is going to predict what's going to happen in the next hour, right? And then so if this was a real time real life application, right, then you'd basically you'd flag, right, the system would flag when the flood threshold reaches a certain level, right? If the predicted flow is bigger than certain threshold, then it's a flood, right? And we should warn. And this gives us if the predictions are accurate, this gives us 1 hour lead time, right? Meanwhile, then maybe that's that's probably very very critical in some cases, right? Could be life saving, right? So
Yeah, we're actually gonna simulate storms tomorrow. So
okay.
we're gonna see this in practice.
Yeah, great. Okay. Right. So again, right. So, and this is a template in a sense for your for the fellows, at least for your capstone project, right? There are data that live in the cloud, right? And you know what you are interested in. Hopefully, we find the data that's suitable for that, right? And you need to set up a cloud system, right? Pull up the data, right? And then do some computation on the cloud, and build a system that does something good, right? So here the example is early warning, right? Okay, so now basically we are all scientists, right? So reproducibility is key, right? So we'll basically share the workflow, right? And somebody who is running something else can also like somewhere else in their machine, or like in some other cloud, right? They can also like reproduce this work, right? So we kind of want to make sure that is the case, right? So like as like I mentioned yesterday, right? So like we want to adhere by this FAIR principle, right? So it's a findable, accessible, interoperable, and reusable, right? We want to make sure the data and notebooks have stable links, right? They have like there's permanent links, right? So that people can find it, people can easily access it, right? So like they don't need to buy a 10,000 machine, $10,000 machine just to access it, right? If that's the case, then the data is not accessible, right? So people should be able to like just like load it in their machine with relative ease, right? It should be interoperable, right? It should like be in standard formats, and like be usable in like open APIs and so on, right? It should be reusable, right? Same environment, same result every time, right? If you run the same code in the same environment, right, you get the same result, right? If Mihail builds a forecasting system, and like if he runs in his machine, the results are good, and if I run it in my my machine, the results are bad, right? Then that's like I don't know what's going on there, right? That's like not very useful, right? So we want to make sure these things are consistent in the data that you eventually release on the cloud, right? Or like the code and the like application that you build over the cloud. Okay, so at times cloud is not the right answer, right? Cloud computing is useful for a lot of different things, right? But at times like we don't want to like all like we do not want to think of as like cloud computing is like solution to all of our computing problems, right? It's not. So if there are like tiny quick jobs, right? If there are jobs that requires like a small analysis, right? Maybe a simple neural network training, right? That takes like very simple, or like you're just interested in building a logistic regression model that you can just do in your local machine, right? You don't need a like a whole like 32 core like 512 gigs machine, right? So just if it's a small job, we can just do it in our local machine, right? If it's a like a very like steady and very big compute, and it's quite stable, right? So for example, like maybe like you are running like a weather service, right? Right, you are going to process the data every day, you are going to run exact same model, right? Or like maybe you update the model, but you are running a model every day, and you're making forecasts for the next 7 days, and it's a like like a repeated process, right? So the exact same computation has to happen every day, every time, right? So then it's better to buy your like build your own warehouse in a sense, right? That's going to be significantly cheaper than renting machines on the cloud, right? And also if like your data is highly sensitive, right? So some restricted data cannot legally leave certain systems. So these include like like in universities student records, right? In hospitals like patients records and so on, they cannot leave like there are some certain like local and also federal level guidelines, right? Like these are like acts, right? That prevent the data from like leaving the system. So you have to like hence you cannot move this data to a public cloud system, right? So like if your application requires a like very sensitive like water science data, then cloud is not the right answer, right? You have to do things either in the system, like the servers that reside within the system, right? Or in local machines that are within the system, right? You cannot move the data away. And also if there is no internet, right, no connectivity, right, the cloud cannot help, right? So for example, if there is a field, right, with no signal, right, and like you want to like go like measure a system, build a system that builds the water, that kind of monitors the water level in a well, for example, right, in a remote location, and it has no internet, like then you cannot do cloud, right? So you have to like so we'll see tomorrow what to do in those situations. Okay, so now let's talk about a little bit about the platform that we're going to use, right? So we are going to use Access and Jetstream, right? So Access basically provides the credit, and Jetstream is the machine, the system that uh, uh, we use, right? So Access stands for Advanced Cyber Infrastructure Coordination Ecosystem Service and Support. It is the program from National Science Foundation, and we're very grateful for the support. So this system gives researchers access to the basically a cloud computing resources, right? And so in a sense, it's not a computer in a sense. It's not a compute system, right? So it is a wallet and the marketplace, right? Basically, it gives they have their tokens, right? They have credits, right? And you can use those credits to rent, then go ahead and rent compute from compute providers, right? So we apply for access credits, right? And by the way, right, because most of you are PhD students and faculty members, I'm sure you can also request for credits through access, right? And once you apply, you get some allocation from access, right? So and basically the credits that you get are the currency of this system, right? So I don't know the exact exchange, but I'm sure, right, we can convert, right, how much AWS charges for same resources, right, that just charges, and then you can bring out the equivalence, right? So the credits are the currency. These are portable, and these credits then can be spent on the real machines, right? So to set up the system we had built for this afternoon, we had to use real credits that Access had provided us, right? And then you pick a resource, right, like a Jetstream or Expanse, right, or Anvil. So these are AWS and Google Cloud and so on, right? So we have picked Jetstream 2. So we take these credits that we have gotten from Access and we spend it on Jetstream 2 by renting the machine, right? So yeah, is there a question, Mihail? You are taking it? Okay, all right. So can everybody see the question and the answer that Mihail provided? Is that the case? Or
I'm
is it
writing it right now.
sorry?
I'm writing it right
Oh,
now.
no, no. I mean, but people can see, everybody can see the questions and answers, right?
I don't think so. I'm not sure.
No,
Oh, yeah, they
okay.
can.
Yep. All right. Thank you. Thank you. Yep. All right. Okay. Okay. So, right. So, so the credits are basically a currency, right? And you can spend it in many different ways, right? So these are kind of think of credits as airline miles, right? This is a money. This is kind of like a money if you use it for flight. Otherwise, it's useless, right? You can't buy grocery with airline miles. And maybe nowadays you can, but back in the day you were not able to, right? In a sense. So so you exchange these access credits for time on whichever resources suit better, right? So we use a Jetstream 2, right, where we have cloud virtual machines and Jupyter Hub, right? If you want large CPU, GPU batches, and you have an SPG jobs, you can use Anvil, right? So these are general supercomputing, right, with a lot of CPU and memory. If you need that, you can use Expanse. If there is a GPU heavy machine learning, right, you can spend this on Delta, right? So the idea is the same. You have this access, right? You have these access credits, and then you have these providers. You ask basically the system to move your credits to one of these resources, right? And then once you have that, you have enough credits to spend and rent the machines and do your computing job, right? So in a sense, this is a marketplace, right? So there are multiple providers. You have the money, you have the credit, right? And you can choose where to rent machines based on your need, right? So you make the decision per task, right? So we chose Jetstream 2 because our goal is to make interactive browser-based cloud computing application, right? And it is built for exactly with that in mind, right? So there's a clean VM model, there's a clean Jupyter Hub support, right? And the credits can be easily transferred to there. Okay, so our machine for the week, it's basically Jetstream 2 is our provider, service provider, right? So we'll rent Cloud VM on Jetstream 2. It's a research cloud based on Indiana University. So it's built for interactive and on-demand science, right? It behaves like a small academic AWS in a sense, right? So the instances that we discussed earlier are like, for Jetstream 2. So there are like, you can basically launch a computer in minutes from a browser, right? So they provide on-demand VMs. I think they have NVIDIA A100s. These are quite powerful, right? NVIDIA A100s are like, very good for LLM training and so on, right? So the GPUs are available. There is Jupyter Hub ready systems, right? And we can pay for things entirely from our access allocations, right? So hence, like, this, we felt like this was the best system for our, like, workshop this week. And I will provide you some credit, like at least the fellows, some credit uh, uh, for their, like, capstone project, right? So they can also do the same. But if they want, they should be free to choose Anvil, Expansor, Delta, right? So that should be possible. But we'll discuss that more. Okay, all right. So how is the translation, right? So one credit means one core hour, right? So one access credit translates to one CPU core running for 1 hour in Jetstream, on Jetstream, right? The exchange will be different on the other providers. That I don't know. Maybe. Yep. So like, our 32 core hub, right? So 1 hour, for 1 hour workshop, we need 32 credits, right? All 3 afternoons, we need 100 credits. Hub per 12 hour per day. If we run it for 2 weeks, we need 3,800 credits. But your application might. So we have around 200,000 credits, right? So I think that's what we have transferred to Jetstream so far, right? So like,
No, we only transferred 50,000 because you want to use the rest for the capstone, right?
okay. All right. Yep. So we have some for the tutorials that we're going to do, and we have reserved some for the capstones for the fellows. Right? So you kind of need to know what you're paying for, right? So one credit essentially means one core hour, but this is for CPU core, right? Do you know, Mihail, what is how much does it, like, one GPU hour costs?
I think it's 3 times more, but I'm not sure.
Okay, right. So if you are using machine learning application and if you use GPU, then you have fewer, essentially, like, you are buying more expensive thing, right? So you should also know that. Okay, so how will work? So we have a one shared hub, right, with 17 browsers, right? You will not install anything today, right? You'll, like, so I hope I've been saying, like, we'll do a lot of these things today, and maybe, like, you're anxious, right? You don't have to. I think it's relatively straightforward, right? We'll run one large VM with a shared Jupyter hub. So, and like, you'll open a link, right? You'll create an account, log in, right? And then you're already computing in the cloud, right? So Mihail has done the hard job of setting everything up. So you'll open a link, right, in any browser, right? Like, that you have. You'll log in, you'll pick a username, you'll set a password, right? And I mean, like, and then you log in, and there is, like, the notebook kernel that runs on Jetstream 2, right? So you'll, like, do some computing, but that computing is done on Jetstream, right? The VM that Mihail has set, right? So you should know that, this computing, like, you see it in your browser, right? But the computation is actually done somewhere else.
We're going to verify that that's the case during the
Okay.
work.
Okay. All right. Sounds good. Okay, so good cloud citizenship, right? So, like, three rules that keep it working for everyone. Shelve when it's done, right? Again, very important, right? A shelved machine costs $0, right? Or zero credits, right? Always shelve at the end of the season, like, session. For today, Mihail is going to shelve it, right? After we are done with the tutorial, right? Like, if you create your own VM instances, right, for your capstone, you should remember to shelve it. Always pick the right size, right? Always share fairly, right? It is one machine for the whole class, right? So we don't want to hog cores or memory. Okay, all right. So I see there are some questions there. uh so I think Rahul is responding to your earlier answer, Mihail. You can take that. Okay. Does that mean we should develop code first and test it before moving it to the cloud for computation? That's question from Hassan. Yes, that's, I think, actually very important, right? I mean, like, so you should, like, usually, like, you test it locally, make sure it works, right? And then you port it to cloud, right? Or, like, if you're working on a, like, for a company, right? Maybe you have your dev box, right? This is like, a machine where you do your development, you develop the code there, right? And then you test it, right? You do all the batch, all the like, like, all sort of tests that you want to do, right, on the local, right, or like your development box, and then you move it to the cloud, right, for like large scale computation. Okay, all right. So like, okay, now where do we go next? Okay, so this is the so basically, like, this is like, a recap, right, of like, what we have talked so far, right? So cloud basically is like, a model, computation model that behaves like a utility, right? Where you like, pay rent in a sense for the machine, pay rent for the machine that you have like borrowed by the hour. Right? And once you're done with your computation, you give it back, right? So the different cloud platforms, right? So like, frameworks, right? Paradigms, right? So IaaS, infrastructure as a service, platform as a service, software as a service, basically distinguish how much of the system management you want to do, right? And how much flexibility you want. Right? If you just want to use a service, then like, we use software as a services framework, right? Where like, things are already built and we just have to use things. But if we want to like, do everything from scratch, right, where we like, install everything that we need and, build our own APIs and so on, we'll use infrastructure as a service, right? So elasticity is the superpower of cloud in a sense, right? You can scale it up, you can scale it down, right? And then you can release, right? So like, basically like you do not pay anything when your system needs to sit idle because you'll shelve it. And when like, your compute needs grow, you can like, scale the machines up. You can rent a new machine depending on how much compute necessity you have. So another thing is like, most of the like large scale data, they are already in the cloud, and like, in a sense we are bringing the code to the data instead of vice versa, right? The other times we write the code first and then we like, feed the data to the code, right? But here, like in a sense, we are like, taking the code to the cloud where the data already lives, right? So the bill, basically the billing is done based on what you have rented, right? And not how you are using it in a sense, right? Once you rent it, let's say you put rent a like, a file bucket, right? But you don't have anything, right? Depending on the volume of the bucket that you have like rented, you have to pay, right? It doesn't matter what's sitting inside the bucket, right? The same for like, the compute instances, right? Let's say you took like 32 core GPU machine, right? With like, I don't know, 128 GB of GPU RAM, and you don't run anything, right? The fact that you don't run anything doesn't matter, right? Because you have already rented it, so you have to pay, right? The provider is going to charge you based on that. Okay, so staying safe in shared infrastructures, right? Again, you have the thing to remember when you're using cloud is this is somebody else's computer, right? And you're just renting it, right? So you have to protect your login, use SSH keys, right? Never share passwords, right? Or like, paste secrets into notebooks, right? So that people can access it, right? Open the minimum, only expo like, keep the ports that your applications needs open, right? By default, close everything, right? Mind your own data, right? Know where the data, know what the data is sensitive and where it is allowed to go, right? Based on that, make your decision, like, which data can live in the cloud and which has to be within the system, right? Of like, your institution. Always remember to clean up, right? Delete jobs and shelve machines, right? That are not needed. Once you are done with the computing, right? Once you have made the forecasts, right? Shelve the machine. Okay. So this afternoon, right? So for our hands-on thing, right? So we'll log into a system, and then first thing we'll do is like, we'll prove that we are in a cloud, right? We'll inspect the remote machine, right? That you were handed, and then we'll pull live USGS data. We'll take the real-time stream flow data from Iowa River right now, right? Based on that, we'll train an nowcast result, and then we'll predict like, next hour of the flow, and then we'll score it based on the NSC data that we get, right? And then we'll scale out, right? So the forecast may many gauges, like, we'll make forecast for many gauges at once and watch it like, how it speeds up, right? The computation. Okay. And what are we going to do tomorrow, right? What if the sensor has no signal, right? So there is like, so the gauges, these river gauges, right, that we take, right? They all are like, distributed across IO rivers, right? So, and like, basically they are sending the signals to the server where the data is being collected, right? Now imagine there's a like, sensor which has no signals, right? So in that sense, the thing that we do today, right, where we shift like every reading to the cloud is not possible, right? So so basically like like if the internet, if like sensor is not, sensor data is not easily accessible in the cloud, right, then we have to push some computation to the sensor itself, right? And that is like essentially edge computing, right? And we'll talk about how to do that tomorrow in more detail. So this is all we have for today, right? And the like so there are some links, right? Access is like allocations.access.ci.org. Jetstream is can be reached through jetstream cloud-cloud.org, right? And this is our like WaterSoft hack email. If you have any questions, right, you can reach out to us there. We still have 10 more minutes, right? And we are happy to take any questions that you have. Okay, if there are no questions, then Vidya, maybe we can have a break. That's 10-minute early break.
Yes, you can have early break and start recording. It
Okay.
seems there is one questions just popped up.
Yes. Okay. What is the proper way to shell machine? Will you show us during the
Yes.
hands-on? Yes, right?
Yes.
Definitely. Yep. We will do that. So I'm very excited for this afternoon, right? And so, I hope you guys are too, right? So, we'll see you guys in approximately 1 hour, 10 minutes then, okay? All right. Okay, there is another question. During monsoon time, cloud are more than how to clean the data set. I think the question is saying like, is there more cloud computing than to just cleaning the data set? Yeah, right. So like, I mean, the cloud kind of like, handles like, depending on what you need, right? Your application lives in the cloud, right? And your application certainly can go way, way beyond just cleaning the data set, right? So, you might want to make forecasts, you might want to like, make like, early trigger systems, you might want to like, put some mitigation steps, right? So all like, some policy recommendations, right? All those things can live in cloud. If we use Sentinel-2 data from River platform. Okay, I'm not super familiar with Sentinel-2 data. Vidya, do you know what Sentinel-2 data is? Is it like a live, like, river level reading system?
I think it's part of
USGS data?
yes, no, part of remote sensing data, if I am correct, because I'm not remote sensing person, but
Yeah, yeah, even if you use this, right? I mean, like, so
yeah,
like, it certainly goes beyond just cleaning the data, right? I mean,
yes,
like,
it is part of like satellite data using European Space Agency's Copernicus program. So it's freely available. So these guys can, in other countries can easily use this imagery data for Earth system observation.
mm, okay. All right. Thanks for those who have said yes. All right. Thank you. So I'll stop recording. I'll pause recording, right? So Vidya, do we stop recording and create a new recording for the afternoon session or just pause?
Yes, you guys pause it.
Okay,
That's
let's go.
All right, welcome back, everyone. So right now we're going to start the workshop. So first of all, let's take a look a little bit at the concepts Dr. Bijaya presented this morning. So here we have the Jetstream instance that I set up. So as Dr. Bijaya said, uh, I'm technically the system administrator for this workshop, and you will be accessing the server as a platform. So technically for you, it's platform as a service, PaaS, right? So the name of the instance is WaterSoft Hack Hub, all right? So is MX32 32. So we have a total of 32 CPU cores, around 125 gigs of RAM, and 60 gigs of storage. Now, how are you going to access this? So we have a public IP address. I'm going to paste it in the chat. And what I want you to do is paste it into your browser and see if you can get to the login page for the Jupyter server. I'll show you as well. All right, it should look something like this. So the problem is, it seems you guys cannot talk into the chat. So can you please let me know in the Q&A if you can access the same page?
Okay, let me also follow along here, okay? So I can
Okay.
try from here.
Perfect. It seems some people did it already.
Okay. Yep, I can see the system.
Perfect. Okay, let me go back to the. Okay, so what I want you to do is you are going to choose a username and you're going to choose a password. So the first time you do this, this is going to act as a sign up. But remember your password? Yes. So the username and password, you are going to choose them, whichever you want. But make sure you remember the password because you're going to be using the same password for the whole workshop for all 3 days.
Mihail, I don't remember the password that I created last time. I'm gonna make a new one. Okay, for
Oh,
this all along. Okay. All
okay.
right.
Seems some people made the accounts. Uh, Dr. Bijay, was your account ASA? I think you're muted.
Yeah, but I don't remember the password, so I'll just
Okay,
put it
okay.
in.
No, no, just to know that,
Yep.
so I can count, because
Yep.
so someone asked, can you put the URL in the chat? So the URL is just the IP address. You can just paste it into the browser, and it will take you automatically to the Jupyter Hub.
Okay. Do you see me now, Mihail? Can you refresh and see the? Okay.
Yeah. I think it should be everyone.
Okay.
Let's see the Q&A. If any of the fellows didn't make it, please let me know in the Q&A so we can continue. Site can't be reached. Oh, the thing is, the Jupyter Hub is served over HTTP, not over HTTPS, because we don't have a DNS address. We don't have a domain name. So, eh, can you check, Moses, can you check if it works on any other browser? Perfect.
So, Moses, were you able to figure that out?
It seems they were, yeah.
Okay, all right, great.
Let me see. I think we should have everyone.
Okay, all right.
Sounds good. Perfect. Yes, so if you use HTTPS, it will take you to an empty Jupyter notebook, yes. Yeah. Right, it should work on Firefox. I'm using Comet, but it should work on most browsers. All right, so I'm gonna assume everyone has it. If you don't, please let me know in the Q&A. Okay. Now, so right now you have access to the Jupyter server, but you don't have the notebooks yet. So I'm gonna paste in the chat a link that's gonna automatically pull the notebooks from a GitHub repository that I made. Okay, I'll also do it here to see. So can you see my screen right now?
Yeah, we can see your screen.
Okay, so if I press that link, oh, it opens it in a different. Okay, let me do it here. So just paste it into your browser, and it's gonna synchronize the GitHub repository to your Jupyter server account. Okay. Just a moment. Oh, interesting.
Okay, I was able to load. Just copy pasting the link.
Good. So someone's asking, please redo. You just have to put this link into the same browser you set up your Jupyter server in Jupyter server account. So due to the fact that we cannot fully interact, I provided the code as well. You have the code in the notebooks, but we will have some challenges at the end, which I will leave for you to do them. I've also solved them, but I will let you write the code for those ones.
And you'll go over the code one by one, right? One line at a
Yes.
time. Right? Okay.
Yes. To make sure everyone's on the same page, because I'm assuming most of you don't have much computer science experience.
Okay, so if is like, is there anybody who's not able to load it? Can you
Yeah, please let us know.
let us know on the Q&A? Okay, I think there's no Q&As.
Right, so it
There's no
seems
queues
everyone.
on Q&As, so I think we can.
Oh,
Okay, a
I
bit.
can write the link here. So yeah, we can wait for you if you want.
Yeah, yeah. Ayobami, were you able to resolve it? So, uh, okay, he's trying to use a second.
I see. Oh, make sure the browser has your Jupyter server
Yeah.
account logged in.
Yeah. So first go to the first URL, right? Login
Yes.
through using the same email and then uh, click on the new link. Okay, I think maybe we can move on, Mihail, right?
Right. Okay. So now your Jupyter hub should look like this. You should have the three Jupyter notebooks and a README, which is basically the distribution repository I created for you. Okay, so let's get started. So today we talked about cloud. Dr. Bijay gave you the presentation. So as he mentioned briefly, we will first validate that we are in the cloud. Then we will pull live river data from USGS. We're going to store it in the cloud to see how storage works. We're going to train a Streamflow nowcast, which is going to try to predict the next hour of flow. We're going to scale out to many gauges to show elasticity. And finally, we're going to learn how to not waste our credits. Okay, so let's get started. So in part zero, first we want to make sure that the code is actually running on the cloud, right? How are we going to make sure that's the case? So Jupyter Notebook uses a program called the kernel. So this kernel is basically what Python, like it's the program that runs the Python interpreter of this notebook, right? So we're gonna start with this system code. So first of all, I'm assuming most of you are familiar with Python. If you're not, please let me know in the Q&A and I can go in more depth if that is necessary. All right. So first of all, we start with importing some libraries. So the OS library. Um, yes. So Rahul is asking if we can do the same thing in Colab or local PC. So yes, you can do it in Colab, but you're not going to have the same output we're having here. You're not going to be on our VM. You're going to be on I think it's a VM that Google Colab uses as well. If you do it on your local PC, it's going to defeat the purpose of the cloud computing workshop. Also, it's probably not going to work because we're assuming the operating system that we are working on is Linux. And most probably, I'm not sure if your local PC uses Linux or Windows or Mac OS. So I would recommend if you can, just try to log in and get the notebook. If not, yeah, you can use Google Colab. Just let us know how it goes. Right. Okay, so going back to our to the code. So first of all, we're going to import three system libraries. They're bundled together with Python. So OS is basically a library that talks to the operating system. Sys is it technically talks to the Python runtime, so it's going to allow us to see some metrics. And platform is the library that allows us to take in machine facts like host name, OS, and so on. And as I said, all of these are shipped with Python. So let's go to the second line. Okay. Now, when we run sys.version, so sys.version is going to write a long string. So it's going to look something like 3.12.6 main and so on. It's going to have a long uh, string. So what we're going to do, we're going to split the string into multiple words delineated by spaces, and we're going to take the first element, which is going to give us the Python version, right? Now, machine hostname. So platform.node basically is going to return the VM's name, which we should be expecting it to be WaterSoftHack Hub, which is the name I gave to this VM. And os.cpu count, as I said, the OS talks to the operating system. It's going to list the number of CPU cores we have. The number should be 32. Okay. Then os.path.expand user is going to give us your home folder, basically. And we know in Linux, we use this symbol, the tilde, to get there. Okay. Now, depending on the setup, like Linux usually uses this setup. So we usually find in proc memo. So what is proc memo? Mem info, actually. It's a virtual file on the Linux server that has as the first line the mem total, which shows basically the amount of memory that is available to us for using, basically. So we wrap it in a try except pattern. Why? Because it might not be available to you at the moment, but it usually is. Okay. We get again, we split it and we get the second element of the array, which is going to give us the number. So it looks something like this, mem total, whatever the number is, space kilobytes, basically. We get those kilobytes. Okay, and we're going to print the available RAM. We divide by 10 to the 6 to get it in gigabytes, and we round it. Okay, let's run it and see what it says. Okay, so it ran extremely fast. We can actually see, yes, the Python version is, I think, the latest. I think this is the latest Python version. Uh, we are indeed on the WaterSoftHack Hub, and we're using this version of Linux. So when I installed it, it was actually Ubuntu. Um, we have 32 cores, and for me, it should show home Jupyter Mihail. For you, it should show whichever. It should show basically whichever user you chose. Okay. And as you can see, there is a lot of RAM available. If you'd like, you can paste your output into the question and answer to see if you get the same results. Does anyone want to share? Nice.
Okay, thanks.
So it seems it's working. Nice. All right. So we've validated that we are on the actual server and we're not running locally. Now, the next thing is we're going to try to pull live water data from the cloud. So you guys are much more familiar with the hydrology dataset tooling, but I could find that the USGS runs a national network of stream gauges and publishes all of these through their free API, basically, from the NWIS, right? So what we will do, we will ask for discharge, basically river flow in cubic feet per meter, per second, I mean. And we're going to use a USGS parameter code to select the gauge. For this example, we're going to use the one from the Iowa River at Iowa City, okay, which is actually a few minutes from our campus here. Okay. So, right. So we're going to build a helper to fetch the real data. And if there's any network hiccups, we're going to fall back to a realistic synthetic gauge that I wrote. And we will see how that goes, right? Now, for the synthetic hydrograph, the fallback gauge I created, okay? So if the live fetch actually fails, we're going to generate 12 days of, 24 days actually, of hourly data. And we're going to do it like this. First, we're going to have a base flow drift. So let's assume the river flows at around 900 CFS. Oh, someone's asking something. Are the 120 gigs distributed to all users? Yes, they are distributed to all of the users. And we'll see actually when we run later, we're going to run something in parallel or sequential, and we'll see it should show. See, we're already spiking a little bit, and we're going to see the elasticity property of the cloud. Okay. So back to the modeling. So for the synthetic gauge, we're modeling it as a base flow drift plus a daily cycle. And I've added three rain events that have like a Gaussian shape. They're like bumps. So three bumps basically. And some noise, some Gaussian noise. Does any hydrologist in the here can anyone tell me basically if you guys are working with models like this, or is this something a little bit far-fetched, or how does your data, like your hydrographs, tend to look like? Anyone? All right.
Okay. So this is only a backup, right? I mean,
Yes,
the
we will
system will
pull
try
real
to get the
data.
real data. If the
Yeah,
real data is not there, then it will use the synthetic model. Right.
exactly. Yes. So Rahul is saying discharge versus time series. I see. Like, what do you mean by discharge versus time series? It's like a time series of the discharge, this queue. Can you elaborate? Right, we will make a graph. We will see the hydrograph. Yes. All right. So let's get into the code. So first, we're going to start with importing the necessary packages. So first of all, we're going to start with requests. So this is the basic Python package for fetching stuff from the web. Then we're gonna go and get NumPy. So NumPy is basically used for fast math on arrays. Basically, it's we can do very fast math with it, and it's customary to call it NP. So we imported NumPy, but we call it NP in the code, right? Pandas is used for data frames, basically tables. So we can build tables of data. And matplotlib is the standard Python plotting package. Okay, so now let's see. Okay, so we're going to have two functions. So anything I write on the Jupyter notebook would be local and won't be changing anything in the WaterSoftHack repository. Yes, yes. So this repository that I made is not the official WaterSoftHack repository. It's just because if I gave you the official one, you would have to copy all of it automatically. But it has also the data from last year, so it would be like there's ML data sets in it, so it would be quite big.
I
Yeah,
mean,
so
it's local in a sense that, it's in your, your like a home directory, your file in the cloud,
yes.
right?
Yes, so if you modify it, no one gets affected. Yeah. And Rahul is asking, yes, yeah, we'll have 24 days, 24 and 24 hours. Yeah, so 756. Yes, exactly. CFS stands for cubic feet per second. Yes, that's correct. All right. So we're going to define two functions. One is for the synthetic stream flow, in which we're going to just encode this formula from here, basically, into code. And one which actually fetches the stream flow from the USGS gauges. Okay, so the first function is going to be called synthetic stream flow. It's going to take in a site the number of days we're simulating, and a seed. A seed is used for randomness. You probably guys are familiar with these things. It's used for reproducibility as well. So if I gave you the same data, you should be able to give me the same output, even if it's random. Okay, so we're going to create a RNG, a random number generator, which is going to do what? It's going to take a seed and it's going to produce a random number, right? Now, if you don't give me a seed, meaning the seed is going to be zero, what we're going to do, we're going to take the site, basically, the site that you put in. So Rahul is saying sometimes he use seed 1, 2, 3. Yes. 1, 2, 3, sometimes 42. Like I've seen a lot of times, 42 is like the standard that's used for NP, NP set seed and 42. It's used like a lot in machine learning. So yes, 1, 2, 3 is also another very common choice. Yes. Oh, so Mayuran is saying, yes, this is like a hydrograph, but not an ideal one for modeling. An ideal hydrograph should start with similar start value and end value, base flow to base flow. I see. Makes sense. Yeah, so what I wanted to do here is basically simulate, like we have a base flow drift, what the river does during the day. We have a daily cycle, and sometimes, there's like a rain event, or tomorrow we're going to simulate a storm as well. So I see. Yeah, it's not the most ideal, but it should work for our purposes. Thank you. So Galina is asking, in general, when you're running some project code using VM, is it advised to create a virtual environment with all the library versions? Yes, it's actually advised. Now, the problem is for you here, you're not going to have to do that because me as the system administrator, I already installed all of the packages that we're going to be using for the Jupyter server. So you don't have to worry about packages. But yes, if you're going to run something inside this VM that requires you to, like you require different packages that you don't have here, you should create a virtual environment which is going to live inside your own user account for this VM. So no one's going to be able to access those packages, but at the same time, you're going to have the base packages plus your virtual environment. Very good question. Right. All right, let's continue. So as I said, if we don't get a seed, we're gonna, like if the seed is zero, which means we don't get a seed, we're gonna take the site, we're gonna hash it. Hashing, what it does, it just basically takes like a string, or takes anything. It can take anything. But what it does, it turns it into a big integer, basically. Okay? Then we're going to take the absolute value to make it positive, and we're going to divide by 2 to the 32 to basically give the random number generator the range that it needs, basically. The random number generator can only generate a number between 0 to 2 to the 32. So 32-bit numbers only. Okay? Yeah. So as I said, we're gonna n will be the number of hourly data points. So it's gonna be the number of days times 24. And IDX, what it does basically, so it builds the timestamps basically. So we're gonna have endpoints, which is 1 per hour. So that's why we use frequency equals 1 hour. Okay. And it's gonna end when? It's gonna end now. So we use timestamp.now using the UTC time zone. This is what this does. Okay. And then we're gonna call them times. So what np.arrange does It basically makes them into an array, basically, an indexable array. Okay. So now let's see how we create the base flow. So the base flow mirrors the equation we have here. Okay, we start with the base 900 CFS, and then we're gonna have 120 times sine. So here, like in Python, you can use two things. You can use math, the math package, which gives you sine, but you can also use the NumPy package, which has its own inbuilt functions. It's much better when you have a NumPy array to use the inbuilt function from NumPy, basically. Okay, so this is the base flow. Now the daily, we do exactly the same thing. Again, we can use the constants. NP also has constants as well, so we can use pi, e, whichever constant you need. Okay, and the bumps, so for the bumps, we do something a little bit different. We're going to initialize them first to 0, and then we're going to create these three centers. So the first center, like where the center of the Gaussian distribution is, the first one is going to be at 25%, the second one at 60%, and the last one at 85%, basically. So there's going to be three rainfall events. Okay, now the flow, we're just gonna add all of these up and we're gonna clip them to 1, basically. We normalize to 1. And we also add rng.normal is gonna give us, we have the random number generator, is gonna give us the noise term. So the output of the synthetic stream flow is gonna give us exactly Q of t. Are there any questions? If not, let's continue. Okay, so now the real stuff. We're gonna fetch the stream flow from USGS, right? So first of all, we're gonna be using the requests library, right? But USGS has like it's a NWIS endpoint, right? So you need when you create a fetch request, you need to set in some parameters. First of all, you need to set the format. We want a JSON like uh, a JSON file to come back. For the sites, we're just going to use one site, and parameter CD basically means we're asking for the discharge. It's the code for the discharge. And the period, it uses this is very standard. Like if you've worked with other data, I don't know, like financial data, all of them also use the capital D. And we want all of the sites basically. Okay, so again, we do a try and accept. We're going to wrap everything into try accept because maybe it doesn't return anything or someone's raising their hand. Just a moment. I think someone was raising their hand. Can you do it again? I think they got shy. Anyways, so this one will basically get us, will output the request. Okay. So it will basically send a GET request if you're familiar with HTTP, how HTTP works. Um, parameter CD, we choose our study area. So when I researched the how it's done, I was looking for the discharge because that's the one we're going to be using in this example. And I found that the parameter CD for discharge is 00060. So I don't know what you mean by parameter CD. We choose our study area. I think you mean the sites. That's the gauge we're actually looking for. Let me know if that answered your question. Right. Okay. So raise for status, what it does, it throws an error if why are we connecting random number generator to a seed number? Oh, just a moment. Yes, river data. river area. Yes, we use sites for that, basically. So why are we connecting random number generated to a seed number? So basically, the seed number is a number that we use. Okay, so think of it like this: when I have a random number generator, every time is going to generate a different number, basically. So if I'm running my code and it generates that random number, and you're running your code and it's generating your random number, then we're going to get different results, right? So for reproducibility, what we do is we set a number, a seed, that whenever we put that seed number into the random number generator, we get the same output, basically. So it's a way, basically, yeah, to set the random number generator to give us the same output to make it reproducible. Sounds good. Okay. Coming back to this, so as I said, the race for status, what it does, it throws an error if USGS returns an HTTP failure. So basically, if they're not serving. So if that's the case, we're going to use the synthetic from above, basically. Right. So, okay, r.json is going to parse the JSON file that we get. So R is going to basically keep the JSON object. Okay. What we want is the value and the time series, basically. Okay. So series 0, basically, we want only the first series that gets back from it. Okay. Then what we're going to do is we're going to take those values and basically make it into a data frame, a table, basically. And we can do PD to datetime, which is basically gonna take the times and transform it into a time index for the data series, a data frame. Okay. And discharge CFS will be a column that stores basically the dates we care about. Okay. This line here is a complicated way of saying I'm going to use the datetime index to basically index the times at which the discharge happened. Okay, and then this happens every 15 minutes. But the thing is, we're working here with hourly data. So what we're going to do, we're going to resample it. We take the mean, we interpolate, and we drop the NA. So we don't drop NA. Most probably, you've done it in machine learning. So we don't like if you have an NA in any kind of calculation, it's going to pollute all of the mathematical calculations that come afterwards. And because of that, it's gonna like everything that touches NA, it's like the plague in computer science. Anything that touches NA becomes NA. So this is just a data cleaning practice. Okay. Oh, Rahul is showing us something interesting. Right. So it seems the parameter CD, depending on what we want, it's gonna give us different like different data series, let's say, basically. Wow, interesting. They have the pH as well. That's pretty interesting.
So this is something you can use for your capstone projects, right? So because we are
Yeah,
doing something specific, right? Other fellows
right,
can use this for some other analysis.
right. I'll keep it here if anyone wants to take a look at it for now. Okay, so if the length is smaller than 48, meaning we just have 48 hours, so 2 days, we raise an error that we don't have enough data points. And if any error is raised throughout this whole process, we just fall back to the synthetic streamflow, right? Okay, this was that was a lot. So we're gonna choose the site is gonna be Iowa City, so the Iowa River at Iowa City, and we're gonna run the fetch streamflow function. Let's see what we get. Okay, so it seems right now in Iowa City, yeah, it's 1:41 p.m. in Iowa City. So it seems the last one we got was at 1 because we're doing hourly aggregation. So basically, so when the clock hits 2 p.m., there's going to be a different one. So it seems we have 337 hourly readings. Rahul is saying USGS only has gauge data for US rivers. Yes, yes, that is correct. Yep. Okay. Now that we have the data and the data is in a data frame, okay, I have the index and I have the data points. So what we're going to do, we're going to plot it basically. And I think you guys are familiar with the way plotting works in Python, so I'll not go over these lines specifically. Let's see how it looks like. Okay, so this is the live stream flow from the Iowa River here at Iowa City. So it seems the last couple of days, the stream flow went down. Actually, yeah, there was a storm a few days ago, wasn't there? Yeah. So it seems it affected the river levels. Okay. Did everyone make it up to here? If you didn't, please let me know in the Q&A. Okay. What have we done so far? So far we validated we're on the cloud. We pulled live USGS data. Now let's see how to store it, actually. Okay, so let's go to part two. So now, Dr. Bijaya talked extensively today on what block storage, how random work here. If you mean uh, the synthetic stream flow, basically. So basically what we do, the randomness is only necessary for this epsilon of t. So we only need it for the noise term, basically. It doesn't, like it's not used in the other stuff is deterministic, basically. So the noise term requires randomness to
Yeah,
simulate.
but I think the fetch stream flow function did not fail, right? So we did
Yeah,
not
yeah, no,
execute the synthetic gauze,
yes.
right? So
We
because we
use the
got the
real data.
real data, we didn't fall back to synthetic.
Yes. All right. So now, we have cloud storage, right? The mo oh, I see. Most of the data sets use object storage, as Dr. Bijay mentioned, but here on our VM, we're going to use block storage because that's the one that's automatically attached to our disk, to the VM, basically. So even from this panel, I can see that the root disk, the one that's connected to this VM, it's mounted on this VM, has 16 gigabytes, basically, right?
60,
60
root
gigabytes.
disk, yeah. Yeah.
Yeah, 60. Yes. Okay. So let's see how to actually, instead of just getting the data and not doing anything with it, let's store it. Let's actually store it on your uh, how's it called? Like on your instance, on this instance. Okay. So Python has a package called pathlib, which basically has how we check how many discharge station in Iowa River. I am not sure actually, but I think if we query the USGS website, we might get a list of all the possible, uh, uh, like all of the ones that are close to Iowa, basically. Yeah, we'll see later. We're gonna have many more, so maybe we can do something like this later. Yeah. Okay. So Pathlib, what it does, it's basically the Python functionality for working with paths. Okay. So first of all, let's get the workspace. So right now, our home directory is not going to be in this folder. It's going to be in the outer folder, basically. So you should have like these three shouldn't exist for you, basically. You only have this WaterSoft cloud folder, and these three notebooks are in it, right? So the home folder is actually one step above, okay? So we're gonna create a file, a folder actually in that home directory called WaterSoftHack Day One Cloud, okay? Now, mkdir make directory basically. If it doesn't exist, it's gonna create it. So that's what it does, okay? Now, for you probably guys are very familiar with data sets and data processing and these things. So basically, we're going to save it in two forms. We're first going to save it as a CSV file, which is human readable, so we can actually take a look at the numbers. And we're also going to save it as a Parquet file, which is much more efficient, but it's not human readable, basically. I see. So Galina is telling us that there is actually a Python library for downloading the data from USGS. Wow. Wow, that's interesting. Make sure for your capstone project, you might want to use this. I'll leave it here as well. Okay. So again, it's good to use try and accept as much as you can in your code because you don't want to mess up if errors happen. I think someone's asking, why other chat not C? I'm not
Uh,
sure.
so like it's in the answered section, right? So there's like a, I don't know if the uh, participants can see the answered questions or not.
Oh, they cannot see the non-answered ones.
Okay, maybe.
I see. So let me just move them there. Okay. All right. Someone found the link for all of the ones and close to IO. Good.
Okay.
It should be an answer as well. Okay, so let's run this and let's see what we get. That was fast. So it saved both the CSV and the Parquet. Of course, it was fast because it's probably in terms of kilobytes. It's very small. So now let's go to the folder and see. As I told you, it's in the home directory. And if I go to the CSV, here we have all of it's basically the data frame stored as a CSV file, similar to an Excel notebook. Yeah. Okay, so now we've stored the data. We have actual block storage that we've used, and from now on, we can use this cache data instead of calling the server on and on, basically. Okay, let's continue. If anyone has any questions up to now, please ask. If not, we can go to part 3. It seems everyone's fine. Okay. So now we have the data. It's stored. How to open the table? Good question. So you see, like if you're looking at my screen right now, if you press on this folder icon, it's going to take you to your home folder, right? So in your home folder, there's a folder called WaterSoftHack Day One Cloud, basically. Okay, if you go into it, you're gonna have this is the Parquet file, and this is the CSV file. If you double click on the CSV file, you should be able to see the table. Sounds good. Okay, now let's go to part 3. So what is a nowcast? You guys are probably very familiar with this, so I'll not go deep into it. Basically, we want to predict the next hour's flow, right? So we want to predict something very close to the present or very close into the future, right? So, what are we going to do? We're going to create a model, a very simple model. We're going to take some features. So, we're going to take the current flow, the last 6 hourly values, an average, and that's it basically. And the target is to predict the change in the flow over the next hour. Okay. We're going to do something very common in machine learning. We split by time. We're going to have a training set, which is usually 70 or 80%. In our case, it's going to be 70%, and a testing set, which is going to be around 30% of our whole data. And we're going to train one of the simplest ML models. It's a random forest. And we're going to score it basically with two scores. First of all, the root mean square error, which is very common in classifiers and forecasters, and NSE, which is what you guys tend to use, it seems. Let me know if you guys actually use this in your workflows. Okay. The NSE, as far as I'm understanding it, is basically how good you're doing relative to just predicting the average, basically. Some form of marginal performance. And the closer it is to one, the better. The closer it is to zero, the closer you're doing to the average. Here's actually the formulas. Now, something very important, and this is done usually in a lot of time series processing. So the thing is, we're lucky in hydrology. It seems the time series are very smooth. But there are other disciplines like, let's say, even like me and Dr. Bijaya, we tend to do epidemiological forecasting, which has curves that are still quite smooth. But there are other domains like financial forecasting in which the curves are very rough, right? So usually what we do, instead of predicting the next data point, we predict the change, basically. Predicting the change is much more stable. And if you guys are familiar with time series processing, we say that it's more stationary, basically. Like the properties of the time series doesn't tend to drift or change. Okay. So we're gonna be using now scikit-learn. So scikit-learn has a lot of models and tools for machine learning, like splits and so on, basically. Now, river flow drifts over weeks, right? So it's still not stationary. Like the statistics of the time series still change, right? So a tree-based model, like a random forest, basically can only predict values it saw in the training, right? So if the river climbs to a new record, a model trained on lower flows would basically undershoot, right? So what the fix is, instead of predicting the next value, we predict the change. Exactly the same trick that's used in other disciplines. Okay. Now the change tends to be stationary. It's still not stationary. I mean, for hydrology, it might be actually, but for other time series, it's usually not. But it's much more stationary than the raw dates. Anyways, we're closing in, so let's go fast. So first of all, let's make the features. So as I said, the features are going to be the lags. It's going to be basically these features: 7 lags, 7 hour averages, and average of the day, basically. Okay. The NSC is basically going to be just implementing this formula into Python. Okay. Then we're going to make a set of feature columns, okay? And then we're gonna store all of these features into a data frame, right? We're gonna do a train test split, which is common in machine learning, right? We're gonna set a model, basically the random forest regressor, which is gonna have 200 estimators, okay? And we're gonna fit the model to the features and outputs, basically. And we're gonna predict the error terms. Let's see how it goes. Wow, that was fast, actually. So we can see the RMSE is not, I mean, it's not amazing, but the NSE is pretty close to 1, which I think it's fairly good actually for such a simple model, right? And now let's plot it. Let's see how it looks like. Okay, it seems we're tracking the flow pretty well, but see when the properties of the time frame changes extremely fast. Here it's like a jump almost, right? The model tends to underperform, which is a known thing in machine learning. Okay. Any questions? If there are no questions, we can go to part 4. Yeah, it seems there are no questions. Okay. So now, doing one gauge is very easy. But what if we have thousands and thousands of gauges? This is where actual cloud comes in power. Oh, someone's asking. If we add 4 or 5 statistical parameter, how justified is our model? Yes, so the more parameters you're adding, the more prone you're to overfitting, which is a big problem in machine learning and black box models. But if your statistical parameters tend to be uncorrelated, I think it's fine for you to add them, basically. And if your model has enough parameters to compensate for how big your number of feature is. Yeah. Okay. Now let's go to part 4. So basically, we're going to do exactly the same thing, but now we're going to be taking, instead of just one gauge, we're going to be taking multiple gauges. So Iowa River at different locations, then the Setter River, Little Setter River, Mississippi, and so on, right? So train site, what it does is going to do exactly the same thing, but it's going to be doing it basically for each site. So let's see how fast this one runs. Okay, now it's fetching the 10 real gauges. It's taking a while. Okay. It fetched them. It didn't store them. It fetched them and basically trained the models. As we can see, the NSE is pretty good. Look at this one. It's almost perfect.
But it's
So
just a 1 hour ahead, right? Yeah.
yeah,
Just okay.
yeah, just 1 hour. Yeah. So pretty good for such a simple model. Okay, now let's see. This is what I want you to see. So let's take a look back here. See, these are you guys basically. Uh, 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 these are you running your workflows on the server. See, we're doing really well because we chose 32 cores. But now I want you, if you can, to press almost at the same time as me. Wait, someone's asking something. Since it's a loop and training it on a single site, how can it be computationally expensive? It's a loop and training is on a single site. It's not extremely computationally expensive. No, it's just that when all of us are doing it in parallel, it's the rate is gonna spike up, basically. That's what I mean. Let me know if that answered your question.
Okay, Mihail, maybe we can do it quickly. We only have
Yeah,
three
yeah.
minutes
Let's
left.
all run it at the same time.
Yeah.
3, 2, 1, go.
Okay, maybe you can look at the usage and see.
Yeah, yeah. It should spike.
Yeah, both
I
RAM
think
and CPU.
it takes time to update. Like it updates probably each minute. So see, it's still running. So actually, someone was saying, yeah, yeah, you can see actually the kernel, but on Google Colab you can see it better. Basically, why did you use random forest for hourly time series modeling? And if the model faces an extreme event outside the training set, would it work? Most probably not. No, random forest. It's not that it overfits, but it tends to overfit. So if it's something it didn't see before, it's probably not going to work. But this is for most machine learning models. Yeah. So it's still running. It's still running. Why? Because we're running all of us both in parallel and sequentially, basically. So while it runs, I mean, let's wait for it to run actually. Right. Someone took a look at it. Let's see. Yeah, it's starting to it's spiking basically, but it updates very slowly.
Okay, I got 45.3 second.
Mine is still running.
I pressed after you, I don't
Yeah, it seems, yeah, I don't know.
synchronization, right?
Right. Anyways, it's fine. Okay. So, okay. Yeah, it took 45 to 48 seconds. When I ran it by myself, it took like 10 seconds. See, so this is the latency of the cloud being used by everyone. Look at the spike. That's how it's supposed to look like. Yeah. So this is the concept of elasticity seen in real time. Okay. Now part five, just be a good cloud citizen for this one. You don't have to shelve your VM because I'm going to be doing it basically, but I'm just going to show you extremely quick how it's done basically. So here in actions, usually you can press the shelve button, and when you shelve it, it's automatically going to stop every running thing on it. Now, be careful when you shelve it, it's going to change the IP address. So I'm not going to shelve it because we need to have access to this for 3 days. But be mindful that when you shelve it, some links might rot. So you need to modify them basically. Yeah. Yeah, we had some optional challenges if we finished early, but it seems we didn't. So I'll let you can do them overnight, you can do them whenever you want, or they're optional. If you don't want to do them, that's fine as well. I'll let the instance run overnight so you can fully play with it. We have enough credits, so don't worry. Thank you. Are
Okay.
there any questions?
Right, we can take questions for 5 minutes. We're at the end of time, and then we'll continue tomorrow.
Thank you as well. Hope you liked it. Yes, you can also do that, but I don't think you can do it on Jetstream. AWS 100% has it. I'm 100% sure they have it. So Yeah.
So Iwami, you don't have to shell right now. So Mihail is the as he showed,
Yeah.
he's the one who is responsible for shelving. But if we if you create your own instance for your capstone, right? Then you have to make sure to shelve it.
Yes.
Okay, all right. It seems like there are no other questions. I think we can stop. Oh, okay, there is one. If we have a large computer, can we break the computer in batches and can run?
Yes.
Yeah,
Remember
that's
Dr. Bijaya talked about batching and streaming yesterday? So you might want to take a look at that.
yeah,
Yeah.
that's possible. Okay, all right. Thank you very much, everybody, for your time. Hopefully, this was useful, right? And if you want to set up your own things on Jetstream, I think that should be possible, right, Mihail?
Yeah, yeah.
And we can also help with that. But if you don't want to do that, and just want to use this system for your capstone, Michael and I, we can also make that help with that, and you can just do your cloud computing coding on, or edge computing coding on IPython. Okay, all right, thank you, and see you tomorrow then. All right.